have had a very therapeutic morning, measuring the lengths of all the leaves on my asparagus plant, and I'm excited to share with you here the measurement of the last leaf. The 377th leaf was 8.21 centimetres long. Great. Now while I take some time to type all of this data into the computer so we can analyse it, I'd like you to have a think of, if we plotted all of these measurements on a graph, what do you think that graph would look like? Okay, I finished typing in all my data. I've ticked it all off, and here it is in GeoGebra. Here's all my data. I've calculated the mean length of leaf was 10.25 centimetres and the standard deviation was 2.09, and I've asked GeoGebra to draw a histogram of it for me. Now this histogram currently isn't very useful because it's only got 3 bars, but what GeoGebra lets me do is increase the number of bars, decreasing the width of each bar. Here we go. Here we go, all the way up to 20 bars. Now maybe this is a sort of graph that you were imagining, showing that we've got an awful lot of leaves. Most leaves are very close to the mean, and it's very unlikely for leaves to be either very short or very long, like outliers away from the mean. Now this shape of the graph is very reminiscent of what we saw for the binomial distribution. It's a bit messy because we've taken this from actual data, it's not a clean random variable, but it looks roughly the same shape. But length of leaves is different to binomial because it's continuous data. These lengths of leaves can be any decimal value between these integers. We did round them here, but if it had been really accurate with my ruler, they could have been any decimal value. So this histogram is just an approximation to a curve. Imagine if I could drag this slider up, all the way up, all the way up, all the way up. So these bars got thinner and thinner and thinner and thinner and thinner. The outcome might look something like this instead. So a curve with its highest point at the mean of our data and sloping off to each side. This is the shape of a normal distribution. It gives the probabilities for a normal random variable. The way the curve is drawn is so that the area under the curve between 2 points gives the probability that our normal random variable will be between those points. So for this case, if I slide these to about 6, about 10, I can work out that the probability of my leaf being between 6 centimetres long and 10 centimetres long was 43.14%. You're going to be using your ClassWiz a lot to find these sort of probabilities, but before we do that, I'd like you to just look at this graph and think of what its key features are. Take a moment and then we'll write some down. Okay, I'll start writing these down. Let's go back here. Key features of the normal distribution. Hopefully, you've spotted that it's symmetrical about the mean. The mean here we're going to call mu. Use the Greek letter mu. That is a probability that we're going to use a lot when working with the normal distribution, so it's useful to write it down. Also, the probabilities tend to 0 as we move away from the mean. Meaning it's really unlikely to get outliers either way. I think it's also worth us writing down that the area under the curve gives us the probability. For example, if I wanted the probability that a random variable was going to be between A and B, then that probability is going to be that blue area there. In the next video, I'll be getting you to calculate a lot of these probabilities if I give you the mean and standard deviation of a normal random variable. I'll end this video with some quick other examples from biology of where normal random variables crop up. I've just snipped this straight from Wikipedia. We were doing the length of a living tissue, our living tissue being leaves, but here are some other examples. If you get bored over the next few days, maybe you can measure the length of all the teeth of your family members and plot it on a graph and see if it does in fact follow a normal distribution.